So, in the last lecture we started studying relative extensions and how relative extensions of number fields. So, k over f, where k and f are both number fields, and we saw how you starting with an ideal in the bottom field, you can construct an ideal in the top field. Starting with an ideal in the top field, there are two ways of constructing ideal in the bottom field. Either you take the intersection or you take the norm, and then we try to study all the relations between some of the relations between these constructions. And we are going to use them today to prove some results about how primes factorize, its degrees, etc. So, let me state a corollary to what we proved last time. Okay. So, let k over f be an extension of number fields okay. Let P contained in OF be a prime ideal, be a non-zero prime ideal, then you can take P OK. This is an ideal, this is a non-zero ideal in OK, and so this will be product of some prime ideals, and we will denote it like this, where P1 up to PR are distinct prime ideals, non-zero prime ideals, and EIs are integers bigger than or equal to 1. Okay, they are natural numbers. All right. And we saw that OK mod Pi is a finite field extension. So, this we have already seen before, of OF mod P. Okay. So, denote the degree of this extension OK mod Pi OF mod P, this degree we denote by Fi, this is called the residue degree, right. Then the conclusion of this theorem is that degree of k over f is summation I going from 1 to r ei fi. Okay. So, there is a very strong relationship between degree of k over f and these exponents that appear in prime factorization of p times OK, and the residue degree and the number of prime factors of p times OK. Okay. All right. So, how do we prove this? I mean, the proof is easy, but this is an extremely useful statement about factorization. Okay. So, the idea is to take norm from k to f of p times OK, right. So, you can calculate it in two different ways. So, firstly, this norm is equal to right. Okay. So, on the one hand, all right, maybe I do not want to calculate it just like this. Yeah, okay. I will compute the norm from k all the way down to q of this ideal. So, this thing is right. So, this thing on the one hand, what I can do is I can take norm from k to f, or first, sorry, yeah, I should write it in the other order. So, let me do that, right. So, what I can do is I can first take norm from F to Q of P I am sorry, I am confusing myself. Why am I doing all this thing? I had it in the correct order the first time around. So, right. So, I can take first norm from K to F of P times OK, and then I can take norm from F to Q. But now P OK is an ideal that that's extended from P. So, you can compute it by using embeddings of F that fix embeddings of K that fix F. So, this will be equal to norm from F to Q of P to the power degree of K over F, okay. And this is same as norm from F to Q of P whole to the power degree of K to F, okay. So, this is one way of computing norm. On the other hand, we can compute norm from K to Q of P OK by looking at the product. So, norm from K to Q of P1 times E1 up to PR times ER, right. This of course is equal to product I going from 1 to R norm from K to Q of Pi times e to the I, okay. And so, consequently, we have to compute what norm of So, I want to compute. So, my claim now is that norm from K to F of Pi is is P to the power Fi, right. So, that is my claim, right, okay. And to prove that claim, again what I am going to do is I am going to look at norm all the way from K to Q of Pi. And what is this? This is the number of elements in OK mod Pi, right. So, let me write it in this way correctly, yeah. So, that is what the definition of this norm is, the number of elements in this finite field. Now, norm from F to Q of small p, this is the number of elements in OF mod P, right. But what is this number of elements in OK mod Pi? This is equal to number of elements in OF mod P whole to the power Fi, right. Okay. And therefore, we get that right, let me to finish the proof I need to right. So, I get norm from K to Q of Pi is equal to norm from f to q of p to the power fi, right. And so, this is norm from f to q, norm from k to f of pi. This is equal to norm from f to q of p to the fi, right. And so, we get norm from k to f of pi is equal to norm from f to q of p to the fi, right. This is what we, sorry, there should not be any norm here. Okay. So, norm of pi down to f is equal to small p to the fi. Now, going back to our equation here, right, I will rewrite this on the next slide. So, norm from k to f of p ok, this is same as product I going from 1 to r, norm from k to f of p, sorry, yeah, I am getting my k's and f's and q's confused. So, norm from k to q, norm from k to q, pi to the ei, but this thing is same as product I going from 1 to r, right. So, norm from f to q of p to the ei fi, right. And so, I can rewrite this as norm from f to q of p to the summation ei fi, I going from 1 to r. So, now you compare this with what we had on this slide, right. So, we compare that with this and we get, so hence we get degree of k over f is equal to summation ei fi I going from 1 to r. Okay. So, it is a very important relation that we get, and we get simply by computing norms in two different ways of this extended ideal p times ok. All right. So, so before we move on to proving more things about this, let me just give you an example. Right. So, let k over q be a quadratic extension. So, degree 2 right. So, degree of k over q is equal to 2. Now, I take p be a prime number, okay. So, p times ok is a non-zero ideal in ok, right, and therefore, it should have factorization into primes. Now, before proving the previous result, we had absolutely no idea how many ways in which how many prime factors this ideal could have. You know, it could have a billion prime factors. We had no idea about what their exponents for each of those prime ideals is. But now we know that p times ok, ok is equal to either P1, P2, okay, P1 not equal to P2, or it is equal to just P with kind of OK mod P degree of this. So, here degree of OK mod Pi over Z mod Pz, this is equal to 1. Here this degree would be equal to 2, or it could be P squared with again the degree of this over Pz. P is equal to 1. So, there are only these 3 possible cases for this prime factorization. So, you see already this is very powerful. Right now we do not have the tools to figure out which case exactly happens for any number field and any prime p, but nevertheless we have already restricted it quite a lot. There are only these 3 possible cases, right. And of course, there are many more cases if you have a larger degree extension. So, for example, if K over Q is a cubic field, then you can have P1, P2, P3 or P1 square times P2 or just P or P cubed, etc. So, as the degree gets larger, of course, there will be more cases, but nevertheless there is a strong restrictions on how many cases can occur. Okay. So, that tells you that is the example for why this result is so useful, even though it is not hard to prove. Now, something even better happens when K over F is actually a Galois extension. So, let us write that as a theorem. Let K over F be a Galois extension of number fields with Galois group G. So, Galois group of K over F is called, I will call it G, right, and then P contained in OF. So, the notation is as above, but let me recall that be a non-zero prime ideal and P times OK, this is P1 to the E1 up to PR to the ER with PI's. So, these are P1 up to PR distinct, pairwise distinct prime ideals, okay, and EI bigger than or equal to 1 natural numbers. Then G acts transitively on P1 up to PR, sorry, not this kind of P, the capital P's, P1 up to PR. Furthermore, the degree of K over F is same as the number of elements in G is same as E times F times G. Okay. So, furthermore, EI's, so furthermore, let me write it this way, oops. E1 is equal to E2 and so on up to ER is equal to E, F1 is equal to F2 is equal to Fr, and I will call that F, and then E times F times R, not G, E times F times R is equal to the order of G, which is of course equal to the degree of this extension. Okay. So, transitive action means for Pi, Pj, there exists sigma in G. So, for each pair like this, there exists sigma in G such that sigma of Pi is equal to Pj, right. All right. So, maybe even before that, I should say that if maybe even before that, for any sigma in G, sigma of Pi is again a prime ideal of OK. So, you can prove that very easily, and so maybe you can take this as an exercise, and sigma of Pi intersected with OF is equal to P. Hence, sigma of Pi is contained in this set P1 up to Pr. So, up to this is your exercise, and so transitive action simply means that any two for any two elements in the set, there exists a group element which takes one to the other. Okay. And this is somewhat tricky in the sense that you can't just start with a pair of P1 and so Pi and Pj and then construct an element in G. Instead, you have to do something slightly different. Okay. So, so maybe I will prove part of your exercise here anyway. So, let P be an element in P1 up to Pr. So, any prime ideal that appears in the factorization of small p times OK, then P intersected with OF, this contains P, right, and 1 does not belong to P intersected with OF because 1 does not lie in P. Hence, P intersected with OF is equal to P, right, as P is maximal. So, I have proven part of your exercise for you, right. Okay. So, what we can do is we can choose, so this is corollary to Chinese remainder theorem, we can choose alpha in P such that alpha, the ideal generated by alpha divided by P is co-prime to small p, right. We can always do that. We proved this as a corollary to Chinese remainder theorem, right. Okay. But if we take norm of this ideal alpha, the element alpha from K down to F, okay, then this on the one hand it belongs to P because alpha belongs to P, on the other hand its norm, so it belongs to F, which means that it belongs to P, right. So, this is same as right, P intersected with OF is same as P intersected with F as that we had that earlier. In any case, so this is in P, which means that if I look at it as product sigma alpha, sigma in G, this is contained inside P, right. And so, sigma alpha belongs to sigma of P, right. So, if I take the ideal generated by, so if I take the ideal generated, so maybe I should write it this way, norm from K to F of alpha O K, right. This is the ideal generated by So this will be contained inside P, right? P times OK. All right. So let me sort of rewrite that as product over sigma in G, sigma alpha times OK. This is contained in product I going from 1 to R, Pi to the EI, right. So each Pi appears in the prime factorization of this ideal generated by sigma alpha OK, right. Okay. But P2, so yeah, so let me we can number them. Oops. Number P1 up to PR such that P is equal to P1. Okay. Now P2 up to PR are co-prime to sigma, so not sigma but just alpha times OK, right. That's how we chose our alpha. Hence there exists sigma in G such that P2 appears in the prime factorization of sigma alpha times OK, and similarly for Pi I greater than or equal to 2, right. Hence G acts transitively, yeah. So hence sigma of P or P1 is contained in P2 for this particular sigma. Therefore, by the exercise sigma of P is equal to P2 because they are both maximal ideals, right. So hence we get the hence we get that G acts transitively. Let me finish the proof. So hence G acts transitively on this set P1 up to PR. So this was first part of the theorem. Now if you take P OK, this is P1 to the E1 and so on up to PR to the ER, right. But sigma of P OK is same as sigma of P times sigma of OK, but they are both invariant under sigma. So this is P times OK, right. Hence E1 and so on, they are all equal and I call them E, right. Now if sigma of P1 is equal to Pj, then sigma induces an isomorphism between OK mod P1 and OK mod Pj. Therefore, their degrees are the same. So over OF mod P. So, therefore, F1 and so on are equal and we call them F. Now, the previous thing we know that degree of K over F is equal to summation EI Fi, I going from 1 to R. But now they are all equal. So, this is summation I going from 1 to R E times F, which is same as E F times R, right. And then of course, because it is a Galois extension, this is same as order of G. Okay, so, in today's lecture, we specifically studied what are the restrictions on the number of prime factors that appear for factorization of a prime ideal in a bigger extension. And we saw that the restriction is even stronger given by this formula here on the at the end that we proved for Galois extensions. Okay. So, we will continue this study in the next lecture. Thank you.